So, first thing we're going to look at, this is our HIV virus. Alright, set up similarly to the flu virus, but a little bit different. What I'm going to show you right now, I'm going to take out all of the proteins on the inside just so we can see them right off the bat. So, we have a little acronym to remember. There are three major proteins in HIV. The acronym is RIP. Right? It's protease. Protease looks like this. We can talk about protease. Just put a quick note in your, make a quick note that it's similar to neuraminidase. Actually, it's similar to neuraminidase in the flu virus, but it's protease, slightly different. And we also have in our virus single-stranded viral RNA. Single-stranded viral RNA. So you'll notice between HIV and the flu are these glycoproteins. They're a little bit different. These GP120 is what they're called. This GP120 has evolved to be perfect fit for what we're going to call oh no, lost my virus. Viral RNA. So it fits, we're calling this glycoprotein receptor. So the GP120 fits into the glycoprotein receptor on the T helper cell. And that allows for the contents of the virus to get moved into the cell. We still have these guys here. Definitely. So GP120, we will call it an antigen. So, someone tell me similarities. GP120 is similar to which glycoprotein on the flu virus? Flip back in your notes. Quentin. That's right, hemagglutinin, yeah, HA. So in its mechanism of action, yeah, similar. So now when we're in, the membrane dissociates and releases, all of its contents into the cytoplasm of the host cell. Right, so these get released, and this gets. So what reverse transcriptase does in the cytoplasm, here's key, in the cytoplasm, it will grab and start attaching and building transcription. So reverse transcriptase, right, initiates and performs reverse transcription. So I'm just going to put the pre-made on there, just so it's a little easier to work with. Then it's going to flip, right, and it works its way back. It'll break this part off, work its way back. It'll work its way back this way. And it's going to create the second strand there. So it's going to end up creating double-stranded virus DNA. So now, this DNA is going to be transported through the nuclear pores into the nucleus of the cell. I believe that's via integrase, is that correct? And this integrase works the exact same as the flu integrase did. So it will come in and it'll cut apart. Oops. It'll cut apart our DNA. This one. Now, for the virus, the viral DNA to be integrated directly into directly into our host genome. From the flu here to exit is the same as on Friday. So our RNA polymerase creates RNA templates of the flu. Those RNA templates are transported out to the ribosomes. Those ribosomes create all of the proteins that are necessary for the replication of the HIV. So protease works the same as the neuraminidase does. So when this is budding out of the cell, it's going to work to help cut out the membrane, pinch the membrane off to allow the budding out to happen. Yeah, duh. Once the viral DNA is integrated into our cells, our HTCs, our helper T cells, if they're healthy, they will continue to live and they will continue to create viruses at a low rate, at a slower rate. So they can still function, but they're basically tricking our cells into thinking that everything is okay. As it's going up through regular transcription, translation, it's unknowingly making these virus particles, creating more HIV particles. All right? As this is happening, we remember what happened to our lung cell. How did our lung cell signal that it was infected? Remember, this is our MHC, major histocompatibility complex, and it's going to show, we'll just use this color to show the same kind of color as the G120. It's going to show that antigen, right? The killer T, yeah. So the killer T cells are going to come, they're going to find this, and they're going to kill that helper T cell. Also another white blood cell that is going to be also aiding in this is your macrophages. When your macrophages, when they see this antigen being presented, they will also phagocytose those helper T cells, the macrophage. So that's two ways that our helper T cells are dying. They get destroyed by the killer T cells, will be phagocytosed by the macrophage, and you'll also get helper T cells that are dying simply because the virus has used up all the resources and it dies, same way as in the flu. So let's just pretend, so I don't have to rebuild it right now for lack of time. Everything is in here still, all right? So I'm not going to put it back in. I just want to show you this right now. So our body, we have these GP120s. Our body starts going through its regular immune response that we saw yesterday, and it creates antibodies for the HIV virus. So these antibodies are scanning your blood, they're scanning your tissues, same with your macrophages. They're looking for the HIV virus to eradicate that virus, just like any other virus that happens in our body. Now, we get to the portion where HIV persists. Reverse transcriptase has no proofreading mechanisms. All right, you need to write this down in your notes. So we know that RNA polymerase and DNA replication, we have systems, proofreading systems that go over our replicated DNA and RNA, scanning for mistakes. So we have proofreading mechanisms to prevent mutation. There is no such mechanism for reverse transcription in HIV. So any mistakes that happen during reverse transcription, they stay with the virus. They stay with the virus. Also, reverse transcription is more error-prone already than DNA replication and RNA synthesis. So we're getting more errors happening, and we have no proofreading mechanism, which means that HIV is rapidly mutating. Rapidly mutating. Let's say this virus particle has gone through a mutation that has slightly changed the G120. It hasn't changed the G120 enough. The shape is still the same, so it can still attach. It can still enter the cell. But it has changed enough, and it's changed the correct portion that these antibodies no longer recognize it. Our immune response that we just built up to that first HIV virus that we contracted is now useless. We basically have to start over again from scratch on a new virus with new antigens, because our immune system, the memory cells that we created, are no longer functioning. So it is going to continue to mutate and mutate and mutate, and our immune system is going to try hard to keep up. But remember, the more helper T cells that get infected, the more helper T cells we lose, the more our immune system becomes compromised, right? And that's what you see if you look at that chart. You see the timeline at the bottom switches from weeks to years. And over years of the virus mutating and changing, you see a steady decline of your helper T cells and a steady incline of the virus particles in your cell, to the point where you contract. It's called AIDS. AIDS is acquired immune deficiency syndrome. So HIV is the precursor to AIDS. You catch HIV as the virus. AIDS is what it's called when you get to the point where your helper T cell count is so low that your immune system is having a difficult time even fending off a basic infection.